Section: Introduction. In this section, we discuss the growing interest in deploying deep learning models, especially large language models, LLMs, due to their strong performance. We note that the auto-regressive nature of LLMs often leads to decode latency being the main factor in inference costs. This latency is primarily influenced by the communication costs associated with transferring model weights from high-bandwidth memory to SRAM or across distributed clusters. To address this, we highlight that quantizing weights and activations can significantly lower the communication load, making it a popular method for reducing inference costs. While floating point representations are standard during training, we find that integer types like int8, int4, and int2 are attractive for inference. However, current quantization methods typically treat each precision level as a separate problem, resulting in multiple distinct models instead of a single adaptable one. Additionally, we recognize that quantizing to very low precisions, such as int2, often leads to inaccuracies. We propose to tackle these challenges by asking if we can train a single model that allows us to derive multiple accurate lower precision models. We affirmatively answer this by introducing Matryoshka Quantization, or MatQuant, a new multi-scale training approach that utilizes the nested structure of integer data types. By slicing the top bits of an int8 quantized weight, we can directly create int4 or int2 models. Existing techniques often overlook this structure, which limits the potential for adaptable models across different bit widths. MatQuant optimizes model weights across various precision levels simultaneously, using shared most significant bits for each parameter and jointly optimizing the loss for each level. This enables us to create a single quantized model that can function effectively at any chosen bit width, providing a range of accuracy and cost options. MatQuant is versatile and can be applied to most learning-based quantization methods, such as quantization-aware training and OmniQuant. We demonstrate the effectiveness of MatQuant by applying it to quantize the feed-forward network parameters of standard LLMs, focusing on improving latency in this critical component. Our results show that MatQuant produces int8 and int4 models with accuracy comparable to independently trained models, while the int2 models generated by MatQuant significantly outperform their individually trained counterparts, achieving 8% higher accuracy on downstream tasks. We also extend MatQuant to quantize all weights of a transformer layer and find that it shifts the quantized weight distribution toward higher values, enhancing int2 performance. Moreover, MatQuant allows for the easy extraction of intermediate bit widths, such as int6 and int3, and enables a flexible accuracy versus cost trade-off by allowing different precisions to be mixed and matched at the layer level. This means we can deploy an effective int3 model even if the hardware only supports int4 and int2. Overall, MatQuant and its variations represent a significant advancement in developing flexible, high-performance multi-scale models, pushing the limits of low-bit quantization for efficient LLM inference. In the related work section, we explore model weight quantization as a crucial technique for adapting resource-intensive neural networks for deployment, particularly for modern LLMs. We categorize quantization algorithms into learning-free and learning-based methods. Learning-free methods use limited data for calibration without gradient descent, while learning-based methods leverage gradient descent to update model parameters or auxiliary parameters for better quantization. We review various learning-free quantization methods, such as min-max and abs-max, which aim to map model weights to the target bit width. Recent improvements have focused on handling outliers with higher precision. While learning-free methods are cost-effective and perform well at higher bit widths, they often fall short in low-precision scenarios, where learning-based techniques excel. Section Summary. In this section, we discuss the challenges of deploying large language models, LLMs, due to high decode latency and communication costs, highlighting the potential of quantization to reduce these costs. We introduce our method, Matryoshka Quantization, or MatQuant, which allows for the simultaneous optimization of model weights across multiple precision levels, enabling the extraction of versatile, high-performance models at various bit widths, including int2, int4, and int8. Section: Learning-based quantization methods. In this section, we discuss learning-based quantization methods, focusing on quantization-aware training, QAT. QAT is a practical method that helps models remain easy to quantize during inference while maintaining high accuracy. However, its use in large language models, LLMs, has been limited because it requires updating all model parameters. Recent advancements have improved QAT's performance and efficiency. For instance, LLM QAT and Bit Distiller enhance QAT by using knowledge distillation from a full precision model. Efficient QAT reduces the time needed for QAT to converge by minimizing reconstruction errors before training. Some techniques, like OmniQuant, take a different approach by only learning auxiliary parameters, such as scaling factors and 0 points, instead of updating the actual weights. OmniQuant learns these additional parameters through gradient descent, focusing on minimizing reconstruction errors, and achieves better accuracy than many QAT methods. Similarly, SpinQuant learns rotation matrices using gradient descent. These learning-based quantization techniques, including OmniQuant and SpinQuant, are popular because they can achieve QAT-level accuracy at a lower cost. We also explore multi-scale training, which has gained traction in computer vision for both recognition and generation tasks. Recently, this approach has been applied to models where the data remains constant, but models of different sizes are trained together. This joint training creates a smooth balance between accuracy and computational requirements, benefiting various applications. Given the success of multi-scale training, we believe it is essential to investigate its application to integer data types, particularly in quantization, to support the deployment of resource-intensive LLMs. We introduce MatQuant, a versatile multi-scale training technique that integrates well with popular learning-based quantization methods like QAT and OmniQuant. As long as model or auxiliary parameters are optimized using gradient descent, MatQuant can be applied across different bit widths, taking advantage of the nested structure of integer data types. In this section, we will explain the fundamentals of QAT and OmniQuant, along with our innovative approach, MatQuant. To summarize the preliminaries, QAT learns a quantized model by optimizing the cross-entropy loss using gradient descent. It employs quantized weights during the forward pass and uses a straight-through estimator to manage gradients during the backward pass. We define the quantization of a real-valued vector in a specified number of bits, where the quantized version is determined by a scaling factor and a 0 point. In contrast, OmniQuant does not update model parameters but instead learns additional scaling and shifting parameters through gradient descent, focusing on minimizing layer-wise reconstruction errors. It also uses a straight-through estimator during optimization. OmniQuant is particularly appealing for resource-limited scenarios, as it operates effectively with less data. It incorporates learnable scales and shifting parameters into its quantization process, aiming to optimize layer-wise errors across the model's layers. Section Summary. In this section, we discuss learning-based quantization methods, particularly focusing on quantization-aware training, QAT, and OmniQuant, which enhance model efficiency and accuracy during quantization. We also introduce our novel approach, Matryoshka Quantization, MatQuant, which leverages multi-scale training techniques to optimize quantization across varying bit widths, improving deployment for resource-intensive large language models. Section. In this section, we introduce MatQuant, a versatile framework designed to create a single model that performs well across various precision levels. It employs a multi-scale training approach compatible with most learning-based quantization methods, such as QAT and OmniQuant. The key idea behind MatQuant is to optimize the quantization loss for multiple target bit widths simultaneously. To achieve a single model that can handle different integer precisions, we nest smaller bit widths within larger ones, taking advantage of the layered structure of integer data types. For instance, to derive a model with a smaller bit width from a larger one, we can extract the most significant bits by shifting them appropriately. Once we establish this framework, we can optimize for various precisions by slicing the most significant bits from the largest bit width we are working with. We define a set of target bit widths and use a quantization function along with a loss function to guide our optimization. Our main goal is to ensure that the model performs effectively across all specified precision levels. In our experiments, we focus on training MatQuant with 3 bit widths, 8, 4, and 2. We also conduct a grid search to fine-tune the loss reweighing factors for each bit width. While our primary focus is on integer data types, we also consider the potential for extending MatQuant to floating-point representations. A significant observation is that MatQuant modifies the distribution of quantized weights across different precision levels compared to the base quantization methods. We notice that the weight distributions shift towards higher values when using MatQuant, which benefits lower precision models like int2. This trend continues up to int8, indicating that the model can adapt to the stricter requirements of lower precision during joint training. Although we specifically train MatQuant for 3 precisions, we find that the model can effectively interpolate to other bit widths, such as int6 and int3, by slicing the int8 model. This interpolation performs comparably to models trained explicitly for those precisions, showcasing the strength of MatQuant. Additionally, MatQuant allows us to apply different precisions at various layers through a strategy we call mix and match. Even without training for these combinations, we can create a wide range of models that balance accuracy and memory usage. Our findings suggest that using higher precision in the middle layers while employing lower precision at the beginning and end is optimal among many possible configurations. We delve deeper into these strategies in the following sections. Section Summary. In this section, we introduce MatQuant, a versatile framework that optimizes a single model for multiple quantization precisions by leveraging the hierarchical nature of integer data types. We demonstrate that this approach not only enhances performance across various bit widths but also allows for effective interpolation and layer-wise precision mixing, resulting in a rich set of models that balance accuracy and memory usage. Section: Experiments. In this section, we present our evaluation of MatQuant, focusing on its performance with 2 well-known learning-based quantization methods, OmniQuant and COT. We demonstrate MatQuant's effectiveness on transformer-based large language models, LLMs, primarily concentrating on weight quantization in the feed-forward neural network, FFN, blocks of the transformer layer. We set our target quantization precisions to be int8, int4, and int2. Additionally, we illustrate MatQuant's flexibility by evaluating it at int6 and int3, and we explore its ability to balance accuracy and cost using a layer-wise mix-and-match approach. We also investigate ways to enhance MatQuant's performance and extend its application to quantizing both FFN and attention parameters. More details on training and evaluation can be found in the appendix. For our experiments, we utilize the Gemma 22B, 9B, and Mistral 7B models. In the OmniQuant experiments, we sample 128 examples with a sequence length of 2048 from the C4 dataset, training with a batch size of 4 for a total of 10 million tokens, except for the int2 baseline, which is trained for 20 million tokens. In the COT experiments, we sample a fixed set of 100 million tokens from the C4 dataset, training all models with a batch size of 16 and a sequence length of 8192 for 1 epoch. Our main baselines for both OmniQuant and COT are models specifically trained for the respective precisions. When we interpolate the models trained with MatQuant for int6 and int3, we do not conduct additional training, while the baselines are trained explicitly for those bit widths. We also compare against a sliced int8 OmniQuant QAT baseline model. For evaluation, we assess all methods based on log perplexity and average zero-shot accuracy across various downstream tasks, using the C4 test set for perplexity calculations and testing on tasks like ArcC, ArcE, BoolQ, HelaSwag, PIQA, and Winagrande. With OmniQuant, we find that MatQuant performs well when used with FFN-only OmniQuant, showing that its average downstream accuracy for int8 and int4 quantization is within 0.5% of the corresponding baselines. Notably, the int2 quantized models of MatQuant outperform the baselines by significant margins for all models. We also observe a drop in accuracy for the quantized int4 and int2 models sliced from the int8 OmniQuant baseline, indicating that the structure of int8 is not fully leveraged. Regarding sliced interpolation, MatQuant allows for bit width interpolation beyond the target quantization levels. We find that the accuracy of the int6 and int3 models obtained by slicing MatQuant models is comparable to the explicitly trained baselines. In our COT experiments, we again see that models trained with MatQuant are comparable to the explicitly trained baselines for int8 and int4. However, the int2 quantized models using MatQuant show improved accuracy over the baselines. The models trained with MatQuant using COT also demonstrate strong interpolative performance, similar to those with OmniQuant. We note that while OmniQuant only trains the necessary auxiliary parameters for quantization, COT updates the weight parameters, which can lead to overfitting to the C4 subset. This overfitting is evident in our results, where log perplexities improve for COT but downstream accuracies decline, emphasizing the importance of high-quality data for COT to be effective. Otherwise, we suggest that users may benefit more from using resource-efficient methods like OmniQuant. Section Summary. In this section, we present an empirical evaluation of MatQuant alongside OmniQuant and COT, focusing on weight quantization in transformer-based LLMs, and demonstrate its efficiency across various bit widths, achieving notable accuracy improvements, particularly at lower precisions. We also highlight MatQuant's ability to interpolate between quantization levels and its performance compared to explicitly trained baselines, revealing that it can effectively balance accuracy and cost in quantization tasks. Section: Layer-wise Mix and Match. In this section, we explore layer-wise mix and match, which, along with its strong slicing-based properties, allows for flexible and interpolative behavior through quantization with MatQuant. Mix and match enables us to create a variety of strong models by using different quantization levels, such as int8, int4, and int2, across different layers. We demonstrate how mix and match effectively covers the trade-off between accuracy and memory cost for the Gemma 29B model, sometimes even surpassing the accuracy of the B-Float16 model. While we have many models, we focus on the best ones derived from our strategy, as detailed in the previous sections and the appendix. Notably, mix and match models with effective bit widths of 3 and 6 achieve accuracy comparable to those obtained through slicing, which opens up new possibilities for effective deployment based on hardware capabilities. Next, we discuss design ablations aimed at enhancing MatQuant. We examine how non-uniform weighting across target precisions affects performance and investigate the co-distillation of lower precision models from a higher precision quantized model. During our efforts to extend MatQuant to all transformer parameters, we discovered a hybrid quantization method that stabilizes the baseline for all transformer weights, which we refer to as single precision MatQuant. We also consider extending MatQuant beyond integer types and the implications for current hardware deployment. When it comes to weightings, we may want to maximize the accuracy of a specific target bit width in MatQuant. We provide a general formulation that allows us to search for optimal weights for each bit width. Our results show that while equal weighting works well, giving higher weights to a specific precision can enhance its accuracy, although it may slightly reduce the accuracy of lower precision models. We view re-weighting as a way to adjust the importance of different bit widths during training, and finding an optimal approach without grid searching is an intriguing research challenge. We also explore co-distillation, where outputs from a higher precision model guide the training of a lower precision model. Our findings indicate that while int8 and int4 models do not show significant improvements, the nested int2 model benefits greatly from int8 supervision, achieving a notable accuracy increase. This advancement allows us to exceed 70% average downstream accuracy for the int2 quantized Gemma 29B model for the first time. In our comparisons, MatQuant performs comparably to explicitly trained baselines for int4 and int8, as well as the interpolated int3 and int6 precisions, while showing significant improvements for int2 models. We conducted an ablation by removing loss terms for int4 and int8, leading to a version we call single precision MatQuant. This version yields a further accuracy boost for int2 models, albeit with a slight drop for int4 and int8 models. The improvement likely arises from the additional bits available during training, allowing for better optimization of the int2 representation. In MatQuant, the need to maintain performance for int4 and int8 slightly hinders int2 performance. However, since int4 and int8 models are usually close in accuracy to the bfloat16 model, we can adjust weights to enhance the int2 model without significantly affecting the others. Our observations suggest that MatQuant and single precision MatQuant provide a more effective approach to low-bit quantization. Section Summary. In this section, we explore the mix-and-match approach, which allows us to create a variety of strong models by applying different quantization granularities across layers, enhancing the accuracy versus memory trade-off for models like GEMMA2. We also discuss design ablations to improve our quantization method, MatQuant, including co-distillation techniques that significantly boost the performance of lower precision models, particularly int2, by leveraging the outputs of higher precision counterparts. Section FFN plus attention weight quantization. In this section, we present our findings on the quantization of feed-forward networks, FFN, and attention mechanisms using quantization-aware training, QAT, as shown in the table. For int8, int4, and the interpolated int6 models, our method, MatQuant, performs similarly to the baseline. However, we observed that int2 and int3 quantizations were quite unstable for both FFN and attention parameters. Most recent studies that apply QAT to these components either use warm starting for the quantized parameters or incorporate additional distillation and auxiliary loss functions. In a straightforward approach that minimizes loss against the ground truth, we found QAT to be very unstable at lower precision levels. In contrast, both MatQuant and single precision MatQuant showed great stability, emphasizing the advantages of MatQuant training. Regarding deployment, current hardware accelerators natively support int8 and int4 quantized models. Additionally, custom CUDA kernels can accommodate various low-precision formats like int2 and int3. MatQuant can produce numerous models during inference. Depending on the deployment environment, we can opt for mix-and-match models or homogeneous sliced models. For instance, if the environment can only support an int2 model due to memory constraints but needs performance similar to an int3 model, we can deploy a mix-and-match model that meets those requirements. Overall, MatQuant effectively covers the memory versus accuracy spectrum, allowing us to find the best performing model for specific constraints. It also opens up opportunities for further research on hardware-software co-design to support flexible bit widths during inference. When it comes to extending MatQuant to floating point representations like FP8 and FP4, we face significant challenges. The exponent in floating point numbers is part of the bit representation and affects the value as a power of 2, leading to exponentially increasing bucket sizes when sliced, unlike the constant bucket sizes in integers. For example, slicing the first 2 bits from int8 results in constant bucket sizes, but this wouldn't hold true for slicing exponent bits from FP8. This area presents a promising direction for future research that could enhance the benefits of MatQuant, even during large-scale pre-training.